Okay, good day, everyone. I want to welcome you to this series of the Minitab training. Today, we're going to continue with what we have started a few days ago on hypothesis testing. Hypothesis testing is very, very important in statistical analysis, particularly if you have collected quantitative data and you want to make conclusion based on the data that you have collected. Then it's important for you to number one, you have to set hypothesis, and after you have set hypothesis, you need to test the hypothesis using the appropriate statistical tool. Now, in hypothesis testing, it also has to depend on the objective of your study. But basically, what we're looking at in this training is just the common methods of analysis that researchers use, and the common hypothesis. And then, so if you are, for example, the last time when we started talking about this hypothesis testing, I talked about the different tests that you can use. But basically, when you set hypotheses, if you have collected samples, you have collected data from samples of different, you have collected data from different samples, all right? And you're trying to compare the means of the samples that you have collected to see whether there are differences between the mean, which one is higher than the other one, which one is significantly higher, which one is not, significantly higher. So if you want to do that kind of comparison, you need to use these appropriate tools. And for you to know whether you're going to use parametric tests or non-parametric tests, you need to test the normality of the data. And when you test the normality of the data, and the data follows normal distribution, then you can go ahead to use a parametric test for your data. And if your data does not follow normal distribution, you need to resort into a non-parametric equivalent of that particular data. Now, you can use different tools based on the number of samples that you are trying to compare. For example, we talked about one sample t-test and two sample t-tests. When you want to use one sample t-test, that means you're comparing one sample, the mean of one sample, with a particular standard, which probably has been reported as the standard for that particular population that you are studying. So you want to see whether your own result is higher than the standard significantly or is lower than the standard significantly. Then you need to use a one sample t-test. Now, if you're comparing between two different samples, but from one same, you are considering one same variable, then use a two sample t-test. Two sample t-tests will help you to compare between two independent samples, samples that are drawn from different populations, but they are still under the same variable. Now, if you are considering more than two samples, and that is when you need to talk about what we're going to be discussing today, which is analysis of variance. Analysis of variance, which is popularly known as ANOVA, will help you to compare the means of more than two samples. So if you have data that has more than two samples, and you have under one particular source or one particular source of variation, maybe one particular variable, then you need to use a one-way analysis of variance. Now, if you're comparing more than two samples of a particular data, but of different variables, you have more than one variable. For instance, if you have two variables, and each of the variable has more than two different sources of, two different samples, then you use a two-way analysis of variance. So, and then by then you can draw out your comparison, and then you make your necessary conclusion. So I'm going to show us in this video how to carry out a one-way analysis of variance, and then also two-way analysis of variance. And then these are the most commonly used methods of comparison of means in statistical in research. Now, so let's bring up our Minitab software. So this is my Minitab software, and I'm going to open a particular example that I've prepared. So let me navigate to the example, to that file. So click File, then Open. Then from Open, I'm going to go to where I have the data. Okay, new data. So Minitab is going to ask me whether it's okay like this, then I will click OK. So now I can draw this up a little bit to be able to see my data. Now, in this data, I want to show you, very briefly, how to identify the variables, or what we call the factors, that we're trying to test and see whether they are influence on the parameters, the things that we have measured, whether the influence of those factors have any significant, kind of difference or not. So like in this particular data now, you will see that I have treatment as a factor, I have fruit type as another factor, then I have days as another factor. And then the researcher went ahead to measure the fruit weight, the number of leaves, the number of flowers, the plant height, under each of these factors. Now, for example, under treatment, there are about 3 different treatments: treatment 1, treatment 2, treatment 3. Then under fruit type, there are about 3 different fruit types: mango, apple, and then orange. Orange is a bit down here. Downward, you can see the orange. And under the days, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 days. So if you want to do this, want to see whether the fruit weights differ significantly with respect to the treatment, whether treatment 1 is the one that produced the highest fruit weight, or it is treatment 2 that produced the highest fruit weight, or it is treatment 3 that produced the highest fruit weight. We need to do this by, since we are looking at treatment as a factor, and if you look at under the treatment, there are about 3 different sources, 3 different samples rather. 3 different samples. You have the treatment 1 is one sample, treatment 2 is another sample, treatment 3 is another sample, and the source of variation is treatment. So if you are considering this source of variation and you have different types of samples under it, then you use one-way analysis of variance. But if you are considering 2 different sources of variation, treatment and fruit type, and each of them has different samples under them, you use a 2-way analysis of variance. So let's start with one-way analysis of variance. Now, to carry out one-way analysis of variance, you need to go to Start, click on Start, then you see ANOVA here, and navigate to one-way ANOVA. So just click on one-way. When you click on one-way, the computer is going to ask you whether the response data are in one column for all factor levels. The answer is yes, because the way I arrange the data, and you also need to know how to arrange data properly, when you're analyzing data. When you're arranging your data, make sure that all the responses that you are testing, the responses mean the things that you measured, the things that you determined, or the things that you counted. Okay, you make sure that they are all in one single column. That is what it's saying. But if you also have them in different columns, Minitab also gives you the room to be able to analyze that data. If you select this now, for example, you will see another option that says response data are in a separate column for each factor level. It means for each factor level, for treatment 1, you put the fruit weight in one column. For treatment 2, you put the fruit weight in another column. For treatment 3, you put the fruit weight in another column. So, but here I have arranged in such a way that all the factor levels, the response data are in one column for all the factor levels. So I did it by arranging the factor levels one after the other. Treatment 1, 1, 1, 1 for treatment 2, 2, 2, 2, treatment 3, 3, 3, 3, all for this fact, because I'm considering 2 different sources of variation. So the number of mangoes that are used are 9 in number. So I divided the treatment in 3 so that they can fit into the number of the mangoes. So you have 3 treatment 1, 3 number of treatment 2, 3 number of treatment 3. When you add all of them together, it fits into the number of mangoes. All right, then you do the same thing for apple, and then so depending on what data you have, you can arrange them in a way that you can still use Minitab to analyze your data. So here is what I have. So the response now, we click inside this box. Our response data is the data that we are trying to see whether it differs, all right, which is the fruit weight now. So I want to use fruit weight for the instance. So I'll double click on this. Then for the factor that I'm working on now is treatment. So double click on treatment, and then it goes inside the box. So let's click on options. Let's see what is there. Option, we have confidence level 95, which is the normal one. 95% confidence level also means 5% probability level. Don't forget that that is the threshold, the least amount of probability level you can use. You can also use 0.0, you can use 1% also, which is 0.01. So 5% means 0.05 significant level, which is what we use. So click OK. All right, then let's check comparison. Now, this comparison is very, very important because we have 3 different samples. So even if we discover that there is significant difference in the fruit weight, the fruit weight differs significantly with respect to treatment, we need to know which of the treatment has this significance level. So this is why we're going to use comparison, and you can use this 2 key. This 2 key is very, very easy to interpret. I will show you later on why it is easy to interpret. When you use 2 key, it's going to group your samples using alphabet. So when you see it later on in the result, I will explain what each of it means. So 2 key is very, very good. You can also use Fisher, also like LSD. You can use Dune. You can use any other kind of thing. Now, so this is what so let's click OK here. I've already selected 2 key. All right, so I click OK. Now let's check graph whether we can see some graphs. So it's telling you can also plot interval plot, you can plot box plot. Box plot is usually used for plotting means to see whether how your means differ. So you can use box plot. You can also plot histogram. You can do any other, So let's just click OK now. And then you click OK. After we're done, we'll click OK. Now let's see what the results has to give us. Now the results, now you can see Minitab even gives us the null hypothesis and the alternative hypothesis. Now, you should remember that null hypothesis is actually telling us that all the means are equal. The means of all the samples in that source of variation, all the means are equal. There is no significant difference between the means. Now, alternative hypothesis tells us that there is significant difference. That means all the means are not equal. So that is what Minitab has done for us. And Minitab is very, very wonderful, in doing that. So, and then it also gives us alpha level, which is 0.05. Now, this is the most important table, which is what we call the ANOVA table. This table will give you what you're looking for. You have the source of variation, which is treatment. You have the degree of freedom. You have the adjusted sum of square, adjusted mean square. You have the F value, and then you have the P value. The P value is the most important thing here, which you need to know whether your sources of variation has significant influence on, on this response value that you response variable that you are looking at. All right, so our P value under this treatment is 0.708. The rule is that when your P value is higher than 0.05, which is the threshold, then there is no significant difference between the means. So in that case, you accept the null hypothesis, which means there is no significant difference between the means. Now, if it is less than 0.05, then that means there is significant difference between the means, then you accept the alternative hypothesis. So let's move down now. Minitab has told us that there is no significant difference. So we don't expect our treatment 1, 2, and 3 to be different. So now let's go under summary. Okay, this summary table actually gives us the mean and the standard deviation. Sometimes if you are preparing your result for publication or you are preparing for your thesis, you will need the descriptive statistics. You remember when we did descriptive statistics, I showed you how to do that. So, but Minitab can do it for you even when you are analyzing using ANOVA. So you have the mean and then you have standard deviation. You can extract this and put them in a table, and then you can, then describe the table later on. So let's go to under the comparison. We use the Tukey pairwise comparison. So let's check what is there. Now, under the Tukey, you see, like I said, the Tukey is very, very easy to interpret. Now, the Tukey has grouping. It has grouped your means using the same alphabet, AAA. All right, so the same alphabet, AAA, means there is no significant difference between the means, the treatment means. So treatment 2 is not different from treatment 1, is not different from treatment 3. Okay, the fruit weights for treatment 2, 1, and 3 are not significantly different from each other. Even though treatment 2 appears to have the highest 5.85, and then treatment 1 has 5.78, treatment 3 has 5.23. The analysis is telling us that statistically, they are not significantly different from each other. So that is why it is good to do statistical analysis, to know whether your values are significantly different or not. Even though logically it looks like it's higher, but statistically it is not significantly different. So whether you use treatment 1 or you use treatment 2 or you use treatment 3 for planting this particular plant, for applying them to the plant, it doesn't make difference in the fruit weight. The fruit weight will still give you almost the same value. That is the meaning of this particular result. So let's check the box plot. The box plot also will show us almost the same thing. You see, even the interval plot shows us they're almost the same. Let's check the box plot. You see, the box plot also tells us that the means are not significantly different. You can see they're almost at the same level. Okay. Now let's check the other source of variation, which is the fruit type, and see whether the fruit type also have something to offer. So let's go back to start. ANOVA, one way. Then here we are going to change. Okay, well, let's leave it at fruit weight, and let's change this treatment to, just delete the treatment, and let's change it to fruit type, which is another source of variation. So double click here. We don't need to change anything here because all we have set is still there. So just click OK. So when we click OK, you will see what we're going to have now. All right, so under the analysis of variance table, ANOVA table, you will see that under this source of variation, when you trace it down, the p-value is 0.002, which is far less than 0.05. And it means that there is significant difference. So we accept the alternative hypothesis. There is significant difference in the fruit weight of all the treatment. So the question now is, where do we have this significant difference? Is it treatment 1 that is significantly higher, or is it treatment 2? So we now have to go to our comparison, which is the Tukey's comparison. So this Tukey comparison now, you can see what we have here. It has grouped this fruit type into different groups, the means. Now, orange has the highest, and it's having A. Apple and mango, they have B and B. What does that mean? It means that the fruit weight of orange is significantly higher than the others, the apple and the mango. So when you consider this as a source of variation, orange has the highest fruit weight, which is significantly higher than apple and mango. But when you look at apple and mango, they have the same alphabet. It means they are not significantly higher they are not significantly different from each other. That is the interpretation of this result. So this is how to do a one-way analysis of variance. You're considering one source of variation at a goal, but each of these sources of variation, each of them has different samples, different levels or different samples. So you are comparing the samples together, okay, and then you now make conclusion. All right, so you can do for any other variable again, you still get your result. For example, if you check for if you're changing the fruit weight now to another, maybe to plant height, for instance, and then you click OK, you still see what you're going to get. For the plant type, you still see that the fruit type has the p-value of 0.000, which is far less than 0.05. So it's still significantly different. There is significant differences among the fruit types, okay, in terms of the fruit weight. Now, there is something that we didn't do at the beginning, which is very important. Like I said, before you can decide on how to use ANOVA, or because ANOVA is a parametric test, you have to be sure that this data follows a normal distribution. So quickly, let me just remind you how to do this. Go to Start. We have done this earlier in the earlier videos. All right, just a quick run. And then go to Basic Statistics, and then go to Normality Test. Under normality test, then you can select this variable that we are working on, fruit weight, and select Anderson-Darley, and then click OK to be sure that we can use ANOVA for it, okay? Just to double sure. All right, so you can see the p-value is 0.19. And if you remember what I mentioned in that video, when you do normality test and the p-value is higher than 0.05, it means the data is normally distributed. So you can use a parametric test for such a data. So don't forget, it's very important when you are testing, when you want to carry out any statistical test to be sure whether you use parametric or not parametric. Okay, I am emphasizing that because many researchers make that mistake by just jumping to ANOVA. Just want to use ANOVA because ANOVA is a popular analysis, even though your work does not agree with ANOVA assumptions. But because ANOVA is popular, you just jump to use ANOVA. So it is not ethical. So it's good to test the data first and then know what to use. All right, let's go to two-way ANOVA. If you're comparing two sources of variation now, not just one source at an instance, you want to compare two sources of variation. How do we do this? So you go to Start. When you go to Start, you come under ANOVA. Under ANOVA, then you now see General Linear Model. It is General Linear Model that you will use inside this Minitab software. Some other software have their own procedures, but in Minitab, you use General Linear Model to bring up your two-way analysis of variance. It will be like as if you are modeling the result, but you are still doing a two-way ANOVA. I'm going to show you how to do that now. So go to Fit General Linear Model, click on it. So when you click on Fit General Linear Model, you're going to have this particular option where you can select what are the response variables. So our response variable here is fruit weight. We want to look at fruit weights. And then our factors, our factor is the treatment, sorry, you delete this. We are going to put it under factor, click inside factor, then bring out treatment, and then bring out, so we are using two different factors. So you have to double click on the fruit type also. So the two factors are here. So let's check under random and tests and see what we have there. Random tests, nothing much. You just leave it or you can close it. Let's check under model to be sure what we have is correct. Yes, the model is okay. This is all you need. Just click OK. Then let's check under options. You still have 95% confidence, two-sided. Everything is okay, no transformation. So just click OK. Then let's go to stepwise, whether there's anything there. Nothing. So it's okay, just leave it the way it is. Graph, you can bring up graphs like you did for we did for the one-way ANOVA. You can also ask it to plot individual plot, histogram, whatever, and then you click OK. And then, okay, so let's click OK now. Let's see what we have. All right, so what we have now is a table that has two sources of variation. You have the treatment as one source of variation, the fruit type as one source of, you can see now we are comparing the two together, all right, the two sources of variation, all right? So now, so under each one, let's check under the p-value. The p-value for treatment is 0.58, which means the treatment has no significant, there is no significant differences in the fruit weight with respect to treatment. You know, we observe the same thing when we are ANOVA, when we consider treatment as a factor. So now under fruit type, you see we have 0.002. It tells us that there is significant, the fruit weight is significantly different with respect to fruit types. Now, I want to show you something that is also very important when you are doing a two-way ANOVA. When you're doing a two-way ANOVA, you are comparing, you are using two sources of variation. You also need to know whether those two sources of variation, whether they have interaction between each other, whether the treatment has interactive effect on the fruit weight, whether the interaction has significant effect or not. So this Minitab has put this under lack of fit. You can see this lack of fit. When you trace it down, you will see the p-value here. The p-value of this lack of fit is to tell you the interaction between the two sources of variation that you are using, the treatment and the fruit types. So here we have 0.305. 0.305 is also higher than 0.05. So it means that there is no interaction between the treatment and the fruit type. So we may not be able to consider that. So our focus now is just the sources of variation. So if the interaction is significantly different, then we can say, oh, okay, maybe the treatment and the fruit type, they have this interactive effect, and then you can then consider it in your interpretation of your result. So let's move down and then check what we have again under whether there is anything again that is important here. All right, nothing here again. So let's now go to comparison, because we need to compare, when we need to compare each of these sources of variation and see where, particularly the one that tells us that there is significant difference, which is the fruit type. We need to know where do we have this significant difference. So we go back to start. We go back to start, and then we'll click on ANOVA. We'll go to General Linear Model again. Now you will see comparison. Before, when we selected General Linear Model earlier on, the comparison was not highlighted. But because we have already run the model, so the comparison became up, it became highlighted, and so we can click on comparison now and select which kind of comparison do we want. We need two keys, all right? And then we're going to, after selecting two keys, then we'll click on this box for each of them. We want to know for treatment, we want to know for fruit type. Then we can also plot the graph. Let's check option, whether there's anything is okay. Graph, we can also plot the interval plot. Click OK, and then that's all. Then you can click OK. All right, so the comparison has come up. So we have comparison for treatment, and you see it's AAA, meaning because ANOVA table already tells us that there is no significant difference with respect to treatment. So you can see all of them AAA. So we can just move downward and see the other one. Even the interval plots are almost the same. So it tells us there is no significant difference. Now for the fruit type, you will see same thing that we had in one way ANOVA. We had orange as the highest and it has A. And then the apple and mango has B. Now, when you check publication, you see some persons, when they have the result, the table of results for their research, they will put alphabet on top of the mean or on top of the standard deviation. Those alphabets are the means of separation. They are to separate the means, rather, is to separate the mean. And that's what we have done here. So you can just put this alphabet on top of the mean or on top of the standard deviation, when you have mean plus or minus standard deviation. So you can just put this alphabet on top of the standard deviation to show the reader that orange is the one that has the highest mean, the highest fruit weight rather, and it is significantly different from apple and mango, because apple and mango, they have BB. They are not significantly different from each other. So let's check the interval plot also. You can see the interval plot is far away. Orange is significantly different from the other one. So that is how this is done. So this is how to carry out a two-way analysis of variance. So you do this by going to the general linear model. All right. So and then from there you can put in the variables, the one that is response, and then the factors also, and then you can run the model, and then you can make conclusion on your result, and then you check whether there is interaction between the variables. So this is where we're going to stop today. I've shown you how to do one-way analysis of variance, and then two-way analysis of variance, and then I've also shown you so many other things in the course of the video. So please go through the video again, and then if you have questions, let's bring it up during the interactive section, the live session that we'll be having later on, and then let us bring it up, and then we can discuss together on it. And then even if the data that I use as an example is a bit not in line with your own area of research, you can also bring up your own data. Then we'll test it whether you can use ANOVA for it or not, and then you'll be able to run it. So whatever question you have, please be free to bring it up during the interactive session. Please, I encourage you to join the interactive session. Please check the schedule, know the time that we're going to be having interactive session, and then you can always come up with your questions. Even if I don't know, we can always share our minds together, and then we can solve the problem together. Thank you very much. And I believe you have learned one or two things from this video, and I wish you a wonderful day ahead. All right. See you during the interactive section. Bye-bye, everyone.